Lecture 2 on a single factor fixed effect model. In a single factor experiment, the experimenter is interested in comparing the effect of treatment, that's levels of the factor, on the experimental unit. For example, an experimenter might be interested in comparing the effect of different teaching methods on the academic performance of students. Suppose that there are K treatments to be compared. Let Yij be the observation of treatment J on unit I. Then the data will appear as in the table below. In this table, T1 represents treatment 1, this is treatment 2, treatment J, and then this is treatment K. These are the observations under treatment 1, Y11, Y21 to YN1. The observations under treatment 2 are Y12, Y22 to YN2. The observations under treatment K are Y1K, Y2K to YNK. The model. The linear statistical model for this design is Yij equal to mu plus tau j plus Eij for I running from 1 to nj and j running from 1 to k, where Yij has defined before is the observation of treatment J on unit I. Mu is the overall mean. Tau J is the J treatment effect. And Eij is the error term. The above model described two situations, namely 1. Fixed effect and 2. Random effect. We shall consider first the fixed effect case. Fixed effect model. In a fixed effect model, the following assumptions are made. Assumption 1. Treatment levels K is fixed. Assumption 2. Sum of treatment effect is equal to 0. That is, sum of tau j as j goes from 1 to k is equal to 0. Assumption 3. Error term is normally and independently distributed with zero mean and constant variance sigma squared. Now, estimation of parameters. Let us define the following notations. Y dot j equal to sum of Yij as I goes from 1 to nj. That is treatment J total. Y dot dot equals sum j from 1 to k, sum I from 1 to nj of Yij. That's the grand total. We estimate the parameters by method of least squares as follows. First, we form the sum of squares of errors. That is S equal to sum j from 1 to k, sum I from 1 to nj of Eij squared. We recall that our model is Yij is equal to mu plus tau j plus Eij. So making Eij the subject, we will obtain Eij equals to Yij minus mu minus tau j. So the sum of squares of errors will now become sum j from 1 to k, sum I from 1 to nj of Yij minus mu minus tau j all squared. Now, for us to obtain the estimate of our parameters mu and tau j, we have to differentiate the sum of squares of error with respect to mu and tau j respectively and equating them to 0. So when we do that, we will obtain the following. If we differentiate with respect to mu and equating to 0, this is the result. Sum j from 1 to k, sum I from 1 to nj of yij minus mu minus tau j equal to 0. Opening this bracket, this will give us double sum of yij, which is the grand total y dot dot, minus double sum of mu. As you sum mu as I goes from 1 to nj, that will be nj mu. Then sum as j goes from 1 to k, that will be equal to sum of nj times mu. And sum of nj as j goes from 1 to k is the total number of observations, which is represented by capital N here. And when you sum tau j as j goes from 1 to k by assumption, that summation is 0. Then we equate this to 0. So that will give us y dot dot minus n mu equal to 0. Solving for mu, that will give us mu hat, that is the estimate of mu, is equal to y dot dot all over capital N, and that is equal to the grand mean. Next, we differentiate with respect to tau j and equate to 0, and that will give us this. Again, when you open the bracket, we will obtain sum of yij as I goes from 1 to nj is y dot j, minus when you sum mu as I goes from 1 to nj, that will give us minus nj mu. Then minus when you sum tau j as I goes from 1 to nj, that will give us nj tau j. Then we equate this to 0. Substituting for mu hat, which is y bar dot dot here, and then solving for tau j, we will obtain tau j hat is equal to y dot j all over nj minus y bar dot dot, and this will give us y bar dot j minus y bar dot dot for j going from 1 to k. Example 1. The experiment was run to determine whether 4 specific firing temperature affect the density of certain type of bricks. The experiment led to the following data. Temperature in degrees Fahrenheit, that we have 100, 125, 150 and 175. These are the treatment, while these are the observations are the density. Estimate the model parameters. Solution. Let us reproduce our data and put the temperature column wise. That's the treatment. This treatment 1, treatment 2, treatment 3, treatment 4. And these are the observations under treatment 1. The total of observation under treatment 1 is 86.9. The total here is 86. Total here is 108.6. And the total here is 86.8. The grand total, that is the sum of all this, is 368.3. Here the number of observations under treatment 1 is N1, which is equal to 5. Under treatment 2, N2 is 4. Under treatment 3, N3 is equal to 5. And under treatment 4, N4 is 4. So therefore, capital N, which is the total number of observations, is equal to N1 plus N2 plus N3 plus N4. And that will give us 18. A, the estimate of mu is equal to the grand total all over capital N. This is equal to 368.3 all over 18. And that will give us 20.5. B, the estimate of tau j, we recall, is given by y bar dot j minus y bar dot dot for j equals to 1, 2, 3, and 4. Let us begin with the first treatment. For j equals to 1, we have tau hat 1 is equal to y bar dot 1 minus y bar dot dot. This is equal to y bar dot 1, that is the mean of treatment 1, is 86.9 all over 5. As the total of treatment 1 is 86.9, and there are 5 observations there. So that will give us 86.9 over 5, then minus the grand mean, which we obtain to be 20.5. So this will then give us minus 3.1. For treatment 2, we have tau hat 2 equals to y bar dot 2 minus y bar dot dot. This is equal to the total observation under treatment 2 is 86, and there are 4 observations there. So the treatment 2 mean is 86 over 4 minus the grand mean 20.5. This will give us 1.0. The estimate of treatment 3 is tau hat 3 equals to y bar dot 3 minus y bar dot dot. This is equal to 108.6 all over 5 minus 20.5, which is equal to 1.2. For treatment 4, the estimate is tau hat 4 equals to y bar dot 4 minus y bar dot dot, which is equal to the total observation under treatment 4 is 86.8, and there are 4 observations there, divided by 4 minus 20.5. That will also give us 1.2. The hypothesis. The hypothesis to be tested in a single factor experiment is set up as follows. H naught is tau j equal to 0 for all j. We are testing this against the alternative H1, that tau j is not equal to 0 for some j. Test procedure. The appropriate test procedure for this hypothesis is ANOVA, that is analysis of variance. The ANOVA rationale. ANOVA consists of partitioning the total variability into its component parts. That is, the total variability is represented by SST naught as sum of squares of total is equal to SST as sum of squares of treatment plus SSE, sum of squares of error, where SST naught is equal to sum as j goes from 1 to k, sum as I goes from 1 to nj of yij minus y bar dot dot all squared. This we can expand and simplify to obtain sum j from 1 to k, sum I from 1 to nj of yij squared minus the correction factor CF, where CF here represent y dot dot squared all over capital N. Similarly, sum of squares of treatment SST is defined to be sum j from 1 to k, sum I from 1 to nj of y bar dot j minus y bar dot dot all squared. Summing over I from 1 to nj, this will give us sum j from 1 to k of nj into y bar dot j minus y bar dot dot all squared. And this we can simplify to obtain sum j from 1 to k of y dot j squared all over nj minus the correction factor CF. Also, the sum of squares of error SSE is defined to be sum j from 1 to k, sum I from 1 to nj of yij minus y bar dot j all squared. This can easily be obtained by subtracting the sum of squares of treatment from that of total. That is, SSE is equal to SST naught, that's sum of squares of total minus sum of squares of treatment. degrees of freedom for sum of squares. There are capital N total observations, so sum of squares for total has n minus 1 degrees of freedom. There are k levels of a factor, so sum of squares of treatment has k minus 1 degrees of freedom. Finally, within treatment J, there are nj observations, providing nj minus 1 degrees of freedom with which to estimate the experimental error. Since there are k treatment, we have sum as j goes from 1 to k of nj minus 1, and this is equal to, when you open this bracket, sum of nj as j goes from 1 to k is capital N, and sum of 1 as j goes from 1 to k is k. So this will give us capital N minus k. So this is the degrees of freedom for the error. Distributional properties of sum of squares. Property 1. Sum of squares of total divided by sigma squared is approximately chi-square with n minus 1 degrees of freedom. 2. Sum of squares of treatment divided by sigma squared is approximately chi-squared with k minus 1 degrees of freedom. 3. Sum of squares of error divided by sigma squared is approximately chi-square with n minus k degrees of freedom. 4. F naught equal to sum of squares of treatment divided by k minus 1 all over sum of squares of error divided by n minus k, which is equal to mean square for treatment all over mean square for error. This is approximately f, as f distribution, with k minus 1 numerator degrees of freedom and n minus k denominator degrees of freedom. 5. The expected mean square for error is sigma squared. 6. The expected mean square for treatment is equal to sigma squared plus sum of tau j squared as j goes from 1 to k divided by k minus 1. The critical region of the test. Notice that 1. In general, mean square for error is an unbiased estimator of sigma squared. 2. Under the null hypothesis H0, mean square for treatment is also unbiased estimator of sigma squared. 3. Under the alternative hypothesis H1, the expected mean square for treatment is greater than the expected mean square for error. Thus, the null hypothesis H0 should be rejected if F0 is greater than F alpha into k minus 1 numerator degrees of freedom and n minus k denominator degrees of freedom. ANOVA table. The above test procedure is usually summarized in an ANOVA table as shown below. So we have source of variation, and we have here between treatment, error, and then total. In the second column we have degrees of freedom. For treatment there are k minus 1 degrees of freedom, for error is n minus k, and for total the degrees of freedom is n minus 1. The next column is sum of squares column. Here is sum of squares for treatment, sum of squares for error, and sum of squares for total. Then here is the column for mean square. This mean square for treatment, which is obtained by dividing this one by this. That's SST over k minus 1 will give us mean square for treatment. And this is mean square for error, which is SSE divided by n minus k. Then the last column is F0, which is MST all over MSE. Coding the observations. The calculations in the ANOVA can be simplified by coding the observations. This is possible as shown in the following theorem. Theorem: if di is equal to xi minus a, then the sum of squares of the deviation of di from its mean d bar is equal to the sum of squares of the deviation of xi from the mean x bar. Proof: sum of squares of di minus x bar as I goes from 1 to n is equal to sum as I goes from 1 to n of, in place of di you put xi minus a, and in place of d bar it is x bar minus a. So minus into x bar minus a will give us minus x bar plus a. Clearly minus a plus a will cancel out, so this will then give us sum as I goes from 1 to n of xi minus x bar all squared. Thus, subtracting a constant from each observation does not affect the corrected sum of squares. Example 2. The experiment was run to determine whether fall firing temperature affect the density of certain types of bricks. The experiment led to the following data. This is the data as in example 1. Does the firing temperature affect the density of the bricks? Solution. Let us code each observation by subtracting 21.5. So if we subtract 21.5 from each of the observation, this will be the result. So the total under treatment 1 will now be 1.2, under treatment 2 is 0, under treatment 3 is 1.1, and the total under treatment 1 is 0.8, and the grand total is 3.1. First, we compute the correction factor CF, which is equal to y dot dot squared all over n. Y dot dot is 3.1, then you square that divided by n, which is 18. That will give us 0.53. Next, we compute the sum of squares for total as SST naught, which is equal to sum as j goes from 1 to k as I goes from 1 to nj of yij squared minus the correction factor. The sum of the uncorrected sum of squares is 1.05, then minus the correction factor, and that will give us 0.52. Sum of squares for treatment is equal to sum as j goes from 1 to k of y dot j squared all over nj minus the correction factor. This is equal to, for treatment 1, the treatment 1 total is 1.2. So you have 1.2 squared all over 5. That's the number of observations there is 5. Plus, for treatment 2, the total is 0, 0 squared over 4. Plus, treatment 3, total is 1.1. So 1.1 squared all over 5. Plus, treatment 4, total is 0.8. We square that divided by 4. Then minus the correction factor, which is 0.53. When we simplify this, this will give us 0.16. We can then compute the sum of squares for error as sum of squares for total minus sum of squares for treatment, which is equal to 0.52 minus 0.16, and this is equal to 0.36. We can then complete our ANOVA table as shown here. Source of variation, that's between treatment, in this case our treatment at the temperature, and then the error total. There are 4 treatment in this example, so the zone of freedom will be 4 minus 1, which is 3. There are 18 observations in all, So 18 minus 1 will give us 17 degrees of freedom. For error, it is n minus k. That is 18 minus 4, which is equal to 14. Or you can subtract 3 from 17 to still obtain 14. So we enter the sum of squares for treatment as obtained before. It's 0.16, for error is 0.36, and for total is 0.52. Then the mean square for treatment is 0.16 divided by 3. That will give us 0.05. For error is 0.36 divided by 14. That will give us 0.03. Therefore, F naught is mean square for treatment divided by mean square for error. That is 0.05 divided by 0.03. That will give us 2.02. Here we are testing the hypothesis H naught tau j equals to 0 for all j. That is, we are testing the hypothesis that the firing temperature does not affect density of bricks. We are testing this against the alternative H1 tau j is not equal to 0 for some j. That is, that the firing temperature affects density of the bricks. Conclusion: at 5% level of significance from F table, we have F with 3 numerator degrees of freedom and 14 denominator degrees of freedom to be 3.34, and the calculated F value F naught is 2.02. This is less than this. Thus the test is insignificant at 5% level. Thus there is no sufficient evidence to reject the claim that the fall firing temperature does not affect the density of the bricks. Thank you for watching. Keep on watching. You will be happy you did. Please kindly click the subscription button for the unlimited access to our lectures.